Dear students, today we are going to discuss a new chapter, which is magnetism. Now, you must have come across magnets in some or other form. The most common form of magnet that is found in your homes is a permanent magnet. So, permanent magnets come in different shapes and sizes depending upon its usage. We have a bar magnet. This is known as a bar magnet. Then we have horseshoe shaped magnet like this. Then we have a toroid shaped magnet, not a circular, we can say circular magnets. As we have seen in our speakers, you might have come across, if you have dismantled a speaker, you would see such type of magnet, which is a circular in shape. So these are various types of magnets that we have encountered because we use it in our day-to-day life. These type of magnets, they are used in various types of equipments that we use in our daily life. Apart from this, we have also seen during our high school that current produces magnet. Supposing there is a current I that is passing through a wire, and if we place a magnetic needle, then it shows a deflection, which means that a current carrying wire produces some sort of magnetic field around itself. So these are the various examples. We'll be going in great details while discussing the permanent magnet chapter. We'll be discussing why the magnets are as they are, because what is a relationship between this type of magnet, which is a magnet produced when a current flows through a wire, and the relationship between the permanent magnets, where we don't see any physical currents flowing in these type of magnets. So what is the correlation between these two types of magnets? There must be something common in between. So we will be discussing all those things. Today, we will be starting a chapter which is magnetic forces. Okay, so what are the magnetic forces and how they occur? We'll be discussing this particular chapter. And to begin with, we'll start with a analogy from the electrostatics, where we have seen that if we have a field, electrostatic field like this, and if we happen to put a charge, that is plus q charge or minus q charge, if there is a plus q charge, it will experience a force in the direction along the electric field. So F over here is equal to q times E. If you put a vector sign over here, it means that the force experienced by a point charge placed in an electrostatic field in the direction of the electric field, if the charge is positive, and this will be opposite to the direction of the magnetic field, the charge is negative. A negative sign will ensure that the direction of the force vector is opposite to that of the electrostatic field. So this can be written alternatively as like this. So this negative of E vector in terms of vector is opposite in sign, opposite in direction to that of the direction of the field. That is, this is E vector, which is along this. Minus E vector will be in the downward direction. So it is just a mathematical interpretation which says that the direction of the force will be opposite to the direction of the field if there is a negative charge placed somewhere in the vicinity of the field. So this is the analogy from our electrostatics. Let's now discuss whether we have something like this happening if we have a magnetic field over here. So this is a B vector. Supposing if we keep a bar magnet, let's say north-south over here, do we have a force experienced by this magnet? So what we will be having over here is that, yes, indeed, we have a force effect over here. And supposing, so in terms of the electrostatic analogy, we have seen that the field is the electrostatic field and charge is the, what do you call, the unit which we have placed over here, over which a force acts. So similar to that, if there is a magnetic field, we have a unit of magnetic field, which is a small magnet, let's say. If you place it over here, it experiences a force. You have seen in your high school studies that indeed it experiences a force. Now let's stretch a little bit and say that supposing there is a magnetic field, and if we place a charge in it, let's say a positive charge somewhere over here, do the charge still experience a force? And the answer will be a big no. That doesn't experience a force if a charged particle is kept within a magnetic field. Now let's say that if we give a velocity to this, if we just push it across or push it along the magnetic field. Okay. So if you have a velocity like this, what does happen? Still, we will find that no force acts upon the charged particle. Now, the velocity will be, or if this particle or this point charge is given a velocity in a direction which is at an angle theta to that of the magnetic field, what does happen? Suddenly we see that this charge experiences a force. Now that force does not lie within the plane of the magnetic field and the velocity. Plane constituted by two vectors, that is the velocity vector and the magnetic field vector. So we will see that the force vector is not along this plane. It is perpendicular to this plane. So a force acting perpendicular to both the vectors v and b, we will draw our conclusion from the study of our vectors that supposing there are two vectors, that is a and b, and if we want to obtain a vector which is perpendicular to these two vectors, then what operation do we perform? The cross product. As we have seen, the cross product of a cross b, that is a c vector, the c vector's direction is perpendicular to both the a vector and the b vector, and its magnitude is given as the magnitude of a into magnitude of b into sine of the angle between the two vectors. Supposing the angle between the two vectors is theta, then we have this relationship. So we have seen from our study of vectors this type of relationship: dot product, cross product. This is known as a cross product between two vectors. Okay. So if there is a force which is experienced by this particle, which is given a velocity in a direction not parallel to the field, we see that a force is experienced by it in a direction which is perpendicular to the plane containing the v vector and the b vector. Now, is this consistent with this cross product? The answer is yes. We will see that if the v is in this direction, is b in this direction, then the field that will be experienced by this is given by this relationship, which is q v cross b. So v cross b is a vector which is coming out of the plane of the whiteboard, and the magnitude part is equal to v vector magnitude into b vector magnitude into sine of the angle between the two. Theta is the angle between v and b. We have this particular relations. Okay, so how does we have seen that it is perpendicular, in direction wise it conforms to the cross product, but we have still to verify whether it depends upon sine theta before concluding that indeed a cross product is the relationship between v and b for the force experienced by the charged particle moving not parallel to the b vector. Now, if it is sine theta or not is furthermore verified by the fact that if theta increases, we have sine theta also increasing. So if we increase the angle, then what does happen? The magnitude of the force also increases. And when it becomes perpendicular to the field, then the force is the maximum, because when theta is equal to 90 degrees, Sine theta value is maximum, which is equal to 1. So again, when by this particular analysis, we have come to the conclusion that the force experienced is indeed governed by the cross product between V and B. So once we have this, let's move on and write a general relationship for the force experienced by charged particle if it is kept in a field which is a mixture of both the electrostatic field and magnetic field. So if we have both the fields, okay, supposing if we have a field like this for electrostatics, and if we have a magnetic field like this, and if a charged particle is given a velocity, or even if it is not given a velocity, due to the presence of the electrostatic field, it will move. If it is a positive charge, it will move perpendicular to the plane of the board, because this direction of the electrostatic field is inward and perpendicular to the plane of the board. So the initial velocity, because a stationary charge can also experience a electrostatic force, therefore it will get initial velocity in this direction, and when it gains a velocity, then suddenly what we find is that the B vector is also able to exert a force on this particular charge. So a combination of these two is written in the form of F is equal to Q into E, this is the electrostatic part, and Q V cross B, this is the magnetic part. So combining these two, we have a force equation like this. Okay, so once we have seen this portion, let's move on and discuss the effect only due to the magnetic field for the present time, and later on we'll be extending it to field where, or a case where both the fields are present, that is electrostatic and magnetic. Now let us discuss, supposing a very simple case, as we have seen in this particular example, that for a charge which is placed, a positive charge or negative charge whatsoever, in a, let's say, magnetic field like this, which is going into the plane of the board, if a charge is given a velocity like this V, then what is the direction and the magnitude of the force experienced by this particular charged particle? So F, as we have seen, is Q V cross B. So this is the relationship between the velocity, magnetic field, and the force. If a charged particle is given a velocity and left, then this force is experienced by it. Obviously we have seen that the force direction will be, this is V and this is B. Okay, so we will align our fingers along the direction of the first vector, which is the B vector, like this, and second vector is into the plane of the board, so like this. Okay, so while finding out the direction of the cross product, what we do is we first of all align our fingers along the first vector such that we are able to fold it in the direction of the second vector, B vector. So if we keep the fingers like this, we won't be able to fold the fingers along the direction of the second vector, that is the B vector. So we have to keep, first of all, our fingers in along the first vector in such a way that we are able to fold the fingers in the direction of the second vector, and therefore a force ensues, that is the resultant vector or the outcome of these cross product results in a vector which is the direction, in a direction which is perpendicular to V and B, governed by the right hand thumb rule. This is the right hand thumb rule. So this is the force which is experienced by the charge. Now what next? We will see that because of this particular force, this velocity, this is perpendicular to the velocity. So what it will do? It cannot change the magnitude of the velocity. As you have seen, a force which is acting perpendicular to the velocity is not able to change the magnitude of the velocity. Then what it will do? It will change the direction of the velocity. So initially its direction is like this. After going over here, suddenly at each and every moment we have just for simplification drawn a distance like this, but at every point of time it will be experiencing a force perpendicular to this. Supposing if we consider this to be very small as we can think of, then at the next point its direction would have changed like this, which is given by the direction of the force. Okay, so force pulls it in this direction, therefore this is able to change the direction of velocity in this direction. Now again the force will be perpendicular to it, so perpendicular to the velocity. So seeing that always the force will be perpendicular to both B and V. So B is already perpendicular, we don't have to do anything because this is lying, the force is lying along the plane of the boat, and as the B vector is perpendicular to the boat, always F and B is perpendicular. So V has to always change such that it is perpendicular to the force. Okay, so if this is the V, the force will be in this direction. Again, this force will change the direction of the velocity, and at a new point the velocity is in this direction. Again we have a force which is perpendicular to this. So if we draw a conclusion from this, the geometrical figure that we will be obtaining is what is a circle. So we have seen in this particular case that if initially the velocity and the magnetic field is perpendicular direction, it is in perpendicular direction, and then we see that the path that is followed by the charged particle is a circle, because as we have seen that the force is always perpendicular to the velocity, and from our study of circular motion we have seen that if the force is a centripetal force, that is always directed towards the center, the velocity being along the tangent direction. So in this case we see that a centripetal force directed towards the center and V is along the tangent will be possible only in case if it moves in a circle or in a helical path. A helical path is a bit, what do you call, involving, therefore we will be discussing it a little while from later. But what ensues from here, that if the force is always perpendicular to the velocity, then the path that is followed by a particle is always a circle. So it will move in a circular motion. Okay. So this much is clear from here. Now, if we have a means by which we can increase the magnitude of the velocity, okay, so the force will no longer be a constant in magnitude. Direction wise it is always varying because centripetal force is force which can be constant in magnitude, but direction wise it always varies. But if the magnitude of the force is also varying, then what we will be having is, if the force increases, then this will be a spiral path. Okay, the pitch of the path will depend upon various factors. We'll be discussing it later on. And supposing if the velocity, supposing this is a B vector and we have a V in this particular direction, then there are two components of velocity. We have a V parallel and we have a V perpendicular. These are the two components of this particular velocity. Now, as we have seen, if the velocity is along the B vector, it doesn't experience any force.